Hello, Math 120, and this is Professor Gonzalez, and I'd like to do some problems from Homework Section 8.5. Now, this section is entitled Exponential and Logarithmic Equations. So, all that practice of looking at properties of logs, writing as a single log, things like that, it comes to good use in trying to solve exponential and logarithmic equations. Now, you know exponential and logarithmic functions are inverse of each other, and so we can use that fact. And so there's multiple ways of actually solving these equations. But the first one, the first rule that this book is kind of throwing at us, it's a good one. I tend to like to use the inverse idea a little more, or using the definition of a log. But they have this one right here, which basically says, number one, complete the following sentence if log base a of m equals log base a of n, then the arguments m equals n. The arguments equal each other. And so this is very, very similar, I should just say, to its exponential, its inverse cousin, I guess, the exponent. Remember, in the exponential world, there was a property similar to this that basically said if you had, I can't remember what variables they used, let's just say if you had a base a raised to the u and it is equal to base a raised to the v, then we could say u equals v. And notice that's kind of a similar idea here with this property, which is called a one-to-one property of logarithms. Anyhow, so we're going to use this idea, number one, to solve some of these logs. And you can see it happen right here at question number 2. And on question number 2, happens real quick, right? Because it says log base 7 of x equals log base 7 of 4. Well, based on that one-to-one property of logarithms we just learned, we can just say that, well, the arguments equal each other, so x equals 4. There's another way to justify this also that I kind of like to talk about, just because it highlights some of the ideas. And that way was so fast, right? You don't want to mess with that too much. But log base 7, right? What's its inverse? Well, its inverse is if you take the base 7 of both sides. Now you've got log base 7 and base 7, log base 7 and base 7, which undo or cancel each other, leaving us with, you guessed it, x equals 4. Okay, so, and another thing always to kind of remember is, remember we're solving for this argument here, and this must be greater than 0, and it is there, so we're good. Keep it going here. Okay, so next one, solve number 3, solve the equation. So what we need to do is we need to apply our rule that a product can be written as an exponent, the product of a log. So this is now going to be log base 6 of x to the second power equals log base 6 of 25. All right. So now when we actually solve this problem, right, we've got the same thing, right? Log base 6 on both sides. So we use our one-to-one property of logs, and we end up getting x squared equals 25. Now we go ahead and square root both sides, and of course when we do that we have to say plus or minus, and this gives us x equals plus or minus 25. Now we go to the original problem. Now this problem is slightly different than the original. If we go to the original problem says this argument that we're trying to solve for, x, must be greater than 0. Well, that gets us, whoops, what the heck, where'd that 25 come from? That's supposed to be just 5, right? Square root of 25 is just 5, plus or minus 5. But going back to my domain, right, is kind of the discussion. Domain, x must be greater than 0, and so therefore that strikes out the negative, right, negative 5. So the actual answer is going to be x equals just 5. Okay, number 4. Well, we've got log base 7 on the left, log base 7 on the right, so the arguments are going to be equal, so therefore we got 5x plus 1 equals 11. We subtract 1 on both sides, so we now have, what is going on with my pencil? Is it pencil or was it me? Anyways, 5, so we end up having 5x plus 1 equals 11. We go ahead and subtract 1 on both sides, and we've got, so 11 minus 1 is 10. We divide by 5, and x equals 2. Okay. Probably worth taking a peek at what our argument has to be, right? Always kind of checking that domain, right? So that whole argument, 5x plus 1, must be greater than 0. So if we subtract 1 and we divide by 5, x must be greater than negative 1/5, and it is, so we're good. Moving on to number 5. Before we actually use our one-to-one property of logs, we have to use this product to exponent idea. We've got the natural log of x to the 1/3 equals, and we're going to do the same on this particular product. This is going to be equals the natural log of 2 to the 3rd. So we've got the natural log on both sides. The arguments must be equal. And we know that x to the 1/3 equals 2 to the 3rd is 8. And one way to undo the 1/3 power is just to raise it to the 3rd power, right? Because then that turns that power into x to the 1st power, and that's what we're trying to solve. Of course, you have to do it on both sides. So we raise the right side to the 3rd power, and we end up getting 8 to the 3rd, which is 512. Whoops, wrong color. 512. And 5, of course, it must be positive, and it is. Okay, so that's good. So we're good to go there. Another way to look at this problem is instead of thinking it as 1/3, x to the 1/3, which I think it's easy enough to just keep it that way. You could remember also this is the cube root of x, would be another way to think of it, which would get us to the same place. How do you undo a cube root? You cube it. And so we'd end up with the same exact answer. Looking at number 6, log base 2 of x plus 3 plus log base 2 of x equals 2. Well, we're going to have to write this as a single log, and we know that we can write the addition of two logs as a product. So it's log base 2 of, and I'm going to write the x first just because it distributes. We usually like to see it that way, but it doesn't matter. And then I'll write that argument second. Now it's a product, right? It's a product, and it equals 2. Okay, now at this point, the way I like to do this is just to remember back to the very first time we looked at logs, and that would be using the definition to convert this to an exponent. So what's the base? 2. Raised to the what power? 2. Equals what? Equals the argument. So this is just x times x plus 3. And that puts us into an equation that should be pretty familiar once we distribute. X squared plus 3x equals 4. Yes, you do have to still remember how to factor. So this is x squared plus 3x. I'm going to subtract 4 on both sides, right? So we got minus 4 equals 0. And we're trying to see what two numbers will multiply to negative 4 and add to 3. Well, that's just going to be x plus 4 times x minus 1. Yep, that'll do that. And therefore, set each factor equal to 0. And when I do that, I get x equals negative 4. Set the second factor equal to 0. Solve it, I get x equals 1. Now we have to be a little bit careful. Let's go back to the original equation. And that argument, x must be greater than 0. So that's going to knock that possibility out. Also, this has to be true. Also, actually you could look at you could use the more restrictive argument. But anyways, you could look at both of them. It has to work for both of them, basically, I guess what I'm saying. So the more restrictive one would work for both. But so x plus 3 must be greater than 0. Subtract 3 on both sides, so x must be greater than negative 3. X must be greater than negative 3, and 1 is still greater than negative 3. So anyhow, we just have one answer left, and that is x equals 1. Let's look at the next problem here. I see we have an addition again, so we can go ahead and take care of this by using the addition of two logs can be written as a product. So this is just going to be log base 3 of x plus 4 times x plus 3 equals log base 3 of 2. So this is the big old argument now. And, well, let's just go back to the one-to-one property of logs, and we got log base 3 on the left, log base 3 on the right, and we can just write this as x plus 4 times x plus 3 equals 2. Multiply that out, and that's just going to be x squared, and we got 4 plus 3 is 7x plus 12 equals 2. Okay, and then I would like to subtract 2 on both sides, so now I've got x squared, well, I said 7x, whoops. So x squared plus 7x, if I subtract 2 on both sides, I have plus 10 equals 0. Now I need to factor. What multiplies to a 10? Multiplies to 10 and adds to 7. Well, I'm thinking that's probably going to be x plus 5 times x plus 2, because 5 times 2 is 10 and 5 plus 2 is 7. Set each factor equal to 0, and that's going to give us x equals negative 5, and set the second factor equals 0, and that gives us x equals negative 2. Now you might think I can't have any negatives for an answers, but wait a minute, what actually is the domain? Let's go back and check it. Let's check this one right here over and do our work over here to the left. And that's basically just saying x plus 4. Yeah, that whole argument expression must be greater than 0, and when I solve by subtracting 4 on both sides, x must be greater than negative 4. So negative 5 is not greater than negative 4, so that's already gone. Negative 2 is greater than negative 4, so that's okay. And when I take a look at this argument, x plus 3 must be greater than 0, so therefore x must be greater than negative 3, and negative 2 is greater than negative 3. So we have a winner, just negative 2. Okay, number 8. Okay, so notice now it's not addition, it's subtraction, and we have a nice property for that. Subtraction can be rewritten as a quotient. So it's going to be 3x plus 3 over x, and all of this still equals 1. So there's our new argument there. And don't try to reduce the x's there, because that would be illegal, because this is addition. If there were factors, I'd be with you, but not with terms, right? Terms are separated with addition or subtraction symbols. You cannot reduce terms, only factors, right? So now what do we do? Well, there's a couple different things you can do, but what I like to do is just use the definition of a log, right? So what's the definition of log? Well, common log has a base 10, if that helps to see that. So we're going to change this to exponential form. So what's the base? 10 raised to the what? First, equals what? Equals this nasty argument in there, which is just 3x plus 3 over x. Well, there's multiple ways of doing this. You can multiply both sides by x. That's probably the best way. You could also cross multiply. That works as well. Let's just go ahead and multiply both of the sides by x. We'd also want to say x cannot equal 0 here, right? So we multiply both sides by x. And now we end up getting 3x plus 3 equals 10x. And now we just go ahead and solve by, let's go ahead and subtract 3x on both sides. And I'm going to take this and write it up here because I'm getting a little squished for space. So now I've got 3 equals 7x divided by 7. And here we go, x equals 3/7. Once again, good to look at these. Now we see x, look at the domain, x must be greater than 0. Good there, 3/7 is greater than 0. How about this argument? And that says 3x plus 3 must be greater than 0. So we subtract 3. We divide by 3, and x must be greater than negative 1. And 3/7 is greater than negative 1, so that is the answer. Okay, moving on to number 9. Number 9, we also have a subtraction symbol. So these two logs can be written as a single log, as log base 2 of x minus 3 over x minus 6. And all of this equals 2. Once again, I think what I would do is just use the definition of log, which basically says I could change this to an exponent. The base is 2 raised to the second power. It all equals this argument right here, which is x minus 3 over x minus 6. Of course, this is x minus 3 over x minus 6. 2 to the second is 4. So you can cross multiply again if you want. You could also multiply both sides by that LCD. So it's kind of your option how you want to do this. Let me just cross multiply on this one, since the last one I did it the other way. So if we cross multiply, right, we cross in this direction, we get x minus 3, and we cross this direction, we get 4 times x minus 6. Let me go ahead and continue to work over here. That's a funny looking arrow. There we go. I've got x minus 3 equals, and let's distribute the 4. 4 times x is 4x, and 4 times a negative 6 is minus 24. Okay, now what? Well, solve for x. Isolate x. And there's so many different ways to do that. I'll subtract x on both sides. We got negative 3 equals 3x minus 24. I'm going to add 24 on the right, so it goes away. I'm going to add 24 on the left, and that gives me 24 minus 3 is 21. How convenient. I divide by 3, and x equals 7. Would be good to look at our domain to make sure this is not extraneous. And I take a look at this guy. X minus 3 is greater than 0, so x must be greater than 3. And 7 is good for that. And I take a look at this guy, this argument. X minus 6 must be greater than 0, so x must be greater than 6. And 7 does work for that as well, so we do have an answer. X equals 7. Moving on to number 10. Number 10, they're asking us to solve this exponential. Now, exponential equations, when you have, we know it's exponential because the variable is in the, is the exponent, right? Notice that x is the exponent. And when you have this situation, in fact, remember way back when we talked about the definition of logarithms, they called this power. Well, yeah, it's a power, okay. It's an exponent. They also call that the answer. Now, why would they call that the answer? Because when you convert it to its exponential form, it's by itself, it's the answer, right? So anyhow, let's go ahead and work this problem down here. And this, what's different about this one also is that they want us to write the exact solution, right? So it's going to have logarithms in it and probably something like that. And then they want us to write the approximate solution rounded to the nearest thousandth place, 3 decimals, okay? There it is right there, 3 decimals, okay. So, all right, well, let's do it. So we've got 9 to the x equals 14. Well, if I want to convert that, remember, now I'm going in the other direction. And I always like to start with a base because the base is the same for logs. That's too big for this base, though. So it's going to be log base 9. There we go. And the argument is going to be what? 14. So let me do that in red. And it equals the power, also known as the answer. Okay. So on this particular problem, for the exact answer, I just put that in. It was a little concerning on the very next one. It was the only one that didn't allow me to put the answer as an exact answer like that. I'll talk about that in a second. But I put in as an exact answer, which is just log base 9 of 14. This is the exact answer. Now, if I want an approximate answer rounded to 3 decimals, I need to put that in the calculator, and we don't have a base 9 on the calculator, right? So we use something called the base change theorem, which we talked about, and we can change this into whatever base we want. But since we want to calculate it, we got to only pick bases our calculator has. There's only two. The natural log ln, so you could use that, which would be the natural log of 14 divided by the natural log of 9. So that'll work. Or also equal is log base 10, which is the common log of 14 over log of 9. And both of those will give us, and we have both those buttons on the calculator, it'll give us an approximation, which is, I rounded to 3 decimal places, it's 1.201. 0.201. Okay. Okay, so then I did the same thing on this one. Not this, well, yeah, it's similar, right? Except the base is a half, which is totally legal. So I have 1/2 to the x equals 7. Okay, and so we just go ahead and do the same procedure, right? Which is, let's write it as a log. So log base 1/2 of 7, man, it's getting a little sloppy here, of 7 equals the exponent x. Okay, and so I put that in for the exact solution, which I would be totally fine with, and it said, yeah, that's right, but we want a different form. And I was like, whoa, okay, because it says to use fractions. Okay, and that's what I didn't use 0.5, I used a half. Anyhow, for some reason on this problem and this problem alone, because all the other ones it was fine, it wanted us to write it specifically like this: the natural log of 7 over the natural log of a half, which is fine because that's what you need to do to put it in the calculator. But I was really surprised that they wanted that for this particular exact value. So if it does this when you're doing your homework, just rewrite it using the base change. But if it does it on the test, that would be a little more annoying because you won't have a chance to change it. In that case, if you put in this answer and it said it was wrong, please email me and tell me which problem it did that on, and I will regrade it and say it's okay, because it is okay. That is the exact answer. But like I said, MyMathLab let us use this form on every other problem except for this particular one, at least when I put it in on my computer. So that was a little bit annoying and weird. Now when I put this in my calculator, I get approximately -2. What numbers is this? So yeah, I did the -2.807. Oh, hey, I also kind of wanted to show you a couple different ways of doing this simple one on number 10. Not to confuse, I just do this just to give you more options. I know some people say, I don't want options, just tell me the way to do it. And the problem is there's not just one way. And I think by showing some options, some people like options, and it also kind of can connect pieces together, I think, in your brain. But if you only want that one way that we just did, which was fine, it'll work, then just that's good. I plug yours or whatever. But here's another way to do it, which I think is kind of cool. So the way the book really loves to do it is this way, okay? So if we had 9 to the x equals 14, right? So what do we do over here? Over here, this way, I use the definition of log to do that one. Well, this way, we're going to use the one-to-one property, one-to-one prop of logs, which we talked about at the very beginning. So, okay, we'll use that one. That just says take log on both sides. And then what do you do? Well, then you have to, see, I don't like this way as much, but the book really does enjoy this way. Then whoops, I shouldn't do that on the same line. Oh, that's not what I want. Stop. I do not want a text box. Just get rid of. Okay, there we go. So we're going to use. Our property of the exponential property, and now the x comes in front, so now it's going to be x times log base 10 of 9 equals log of 14. And now, actually, this is not using the one-to-one. Is this using the one? This is not using the one-to-one property. Let me get rid of that. We didn't use that. So now what we want to do is solve for x. So we just go ahead and divide by log base 10 of 9. And you've got to do it both sides. Log of 9 on both sides. Oh, man. I hate this thing sometimes. So then we reduce the common factor of log of 9. Leaves us with x equals common log of 14 divided by the common log of 9, which you can see that is the same answer I got right there, okay, as an exact solution. All right, so there's that. And I've got one more for you. And this is probably my favorite right here. This is 9. I know it's pretty sad I have a favorite, isn't it? Anyways, but 9 to the x equals 14. So what I like about this next way is that notice up here, we took the log of both sides, and most people just take the common log because, well, they have that on the calculator, right? But kind of a tricky way is to realize that the base is 9, and if I take log base 9 on both sides, well, the log base 9 and the exponential base of 9 will just inverse and disappear, leaving us with x equals log base 9 of 14, right? And that is the exact answer. In fact, you can see that over here, right? And then you could use the base change if you wanted to put it into the calculator, just like we did back using natural log or log base 10. All right, so I gave you a little extra information. You probably raise your hand if you just hit fast forward and went as fast as you could through this video. Anyways, that's extra stuff, so take it or leave it. Now, next one, solve the equation. Okay, so now we have e to the x. It's still, going to be a great candidate for using a log because the variable I'm trying to solve is up there in the exponential position. So let's rewrite it down here. Now let's just use the definition of log. And of course, I just showed you a bunch of tricky ways to do it, right? You could take the natural log of both sides, and that'd be awesome. That would show me, inverses and stuff. But you could also just use the plain old definition. Definition would just say, well, the base in the exponential is right there is e. So as a log, it's got to be log base e of 12. Grab that there. And that's going to be equal to x. Okay, and whenever we have log base e, we don't just write it as log base e. It has its own special name. It's called the natural log of 12, which is the same as log base e, right? So the exact answer is natural log of 12. Then I put that in my calculator, and I round it to 3 decimal places, and I get 2.485. Once again, you're going to find the button that says ln, which is the natural log. Now let's go to number 13. Solve the equation, express your answer in the exact form and as an approximation. Round it to 3 decimals. All right. Hey, by the way, way back when we first started looking at exponents, remember a lot of the problems were problems like, like 2 to the x equals 16, and you're like, ooh, well, let's see. And I could guess and check that. Oh, 2 to the 4th. But what they wanted us to do is to rewrite 16 as a base of 2. And once the bases are the same, well, then the exponents are equal. Remember that? Okay, well, all that was great. But what happens when you have this problem now? uh-oh, right? This problem is 10 to the x equals 29. Now this is the same kind of problems we were having back here. But anyways, I just want to point this out. Back at the very first lesson, we'd say, okay, base is 10. Can I make 29 a base 10? Whoops, you can't. See, and so that really shows you the real necessity for logarithms, because logarithms will help us solve this, right? If you're thinking about this, well, 10 to the first power is 10. 10 to the second power is 100. Ooh, okay, the answer must be between 1 and 2 and probably closer to 1. Yeah, so you're kind of thinking about it, right? So I'm trying to figure out what value of x will get me 29. It's not 1, which is 10, and 10 to the second is 100, not that. So and it looks like it's a lot closer to 10, so it must be close to 1. Well, the logarithms will dial it in for us. Let's convert our base, exponential value. So base is 10, so we've got log base 10 of 29. And of course, all of that will equal the exponent of x. Okay, and like I said, strangely enough, it was totally fine with this, as it didn't, just that one problem it wanted us to write it as the change in base form. It was very strange. So I just plugged this in. Now you don't have to put the 10 in, right? Because everybody knows log base 10 is just a common log. So you just write it like that. Now we do have the log base 10 button on our calculator known as a common log. So you just punch it in. Of course, it looks like this. And you hit that button, you type in 29 and hit enter and round it to 3 decimal places. And we get 1.462. Hey, well that's rounded, right? So it's not going to be exactly right. But if you put that answer in for x, and you said 10 to the 1.462, it's going to be very, very close to 29. Not perfect because we rounded it. Okay, but that's what the logs are doing for us. It's helping us answer those exponential questions when you have a variable that you're solving for that is up there in the exponent position. Okay, so let's take a look at this one. 5 raised to the 4x equals 19. I mean, it's the same kind of philosophy here. Let's just go ahead and just change this. Now, I showed you different techniques, so I showed you 3 different ways of doing this, and I don't care which way you do it, but here's the base of 5. It's nice to know 3 ways, though, because sometimes you want to use another way to get yourself out of a jam when you're doing this stuff. But anyways, we're converting it. So log base 5 of 19 definitely is going to equal the exponent here, which is 4x. Okay, so that's not too bad. We just have to solve for x, so we're going to divide both sides by 4. And there is your answer. Usually, that's actually probably one, well, usually we write the answer, instead of divide by 4, multiply it by a quarter, so it's just cleaner. But they both mean the same thing, so it's 1/4 log base 5 of 19. So 1/4 log base 5 of 19. Okay, now we need to get an approximation. So to do that, we have to do a change of the base, all right? So you could change it to log or to natural log. I'm just going to go natural log of 19 divided by the natural log of 5. And now either multiply it by 1/4, but in the calculator, after you've already calculated that and hit enter, it's probably easier just say divide by 4, I think, or just multiply it by a quarter, but then you got to, okay, a quarter, 1/4 is 0.25, whatever. You know, get you the same answer either way. But here we are. Which one? Where am I at? So when I approximate this, I got about 0.457. All right, now let's take a look at this next one. Okay, so solve the equation, express irrational solutions in exact forms, and as a decimal rounded to 3 decimal places. So, well, let's just write it down again and work it out. So we've got 4 times 3 to the x plus 3 You know, we're trying to isolate x. So, of course, we can subtract 3 off both sides. Okay, so now we got 4 times 3 to the x equals 5. Well, of course, we can divide by 4 because that reduces, giving us 3 to the x equals 5/4. And now we're stuck. 3 to the what power equals 5/4? Well, that's where logs come in. Remember, the base of the exponent is the base of the log. So it's going to be log base 3 of 5/4. And that is going to equal the exponent x. Okay, so that is the exact answer. Log base 3 of 5/4 is the exact answer. And then the approximate answer, of course, in order to do that, we need to change it to common log or natural log. I'm just going to go to natural log. Natural log of 5/4 divided by the natural log of 3. When you put that in the calculator, you get approximately, where am I at? Natural log of 5/4 divided by natural log of 3, 0.203. 0.203. In fact, we can check real quick right now, just to kind of tie this in our head a little bit. Remember what we just did? Well, we had 3 to the something power. Now we did round it. So it's not going to be exactly equal to 5/4. And remember, 5/4 is also, we could think about 5/4 as, what, 1 1/4. Okay, so now let's go ahead and try, just as a, it's not a perfect check because there's some rounding going on, but it's kind of good to kind of tie it into our heads. What do we just do? Right? What did we just do? We just figured out what that is, at least approximately. So if I put this in my calculator, 0.203, and now we're checking, right? And this is, as a decimal, 1.25. And I put 3 raised to the 0.203, and I'm getting 1.24984 ... So see, we almost got there to 1.25, but we rounded it, so we couldn't get there exactly. So that feels like a really good answer. It's right on the, I mean, it's not right on the money, but it's close as it really can be when you start rounding. All right, now let's move on to the next. We flip the page to number 16, and there's another problem to work on here. Now notice with these problems, those exponents, yeah, we're all good there. Let's take a look at this one. This is going to be -5 times e to the x equals -30. So of course we're going to come along here and divide by -5, which is going to give us e to the x equals +6. So now, how can we do this? You can use the definition of logs as the way I've been doing it, or you can be a little bit tricky and just take the natural log of both sides, right? That would do it as well, but I guess I'll just stick with that one way just for now. So if I stick with that one way would be, which I don't always like to just stick with one way, but I'll stick with one way right now. And it's going to be log base e of 6 equals the exponent. So this, we just did this technique using the definition of log, and we all know that log base e really is just the natural log of 6. There's my exact answer. Natural log of 6, and I put that in the calculator, and I get approximately, rounding it to 3 places, I get approximately 1.792. 1.792. Okay, now they're getting a little tougher. So we're solving exponential equations here. Now we're back to logarithmic equations. All right, well, I see that I have an addition of 2 logs with the same base. So I can rewrite that as log base 2 of x minus 2 times x. I think I want to put it in front there. Okay, and that got a little bit squished. And it says that all equals 3. So the arguments get multiplied together. So now we have, Let me rewrite that 2 there, just so it's not so squished there. Okay, so now we have a log, and we're trying to figure out the argument. And in this case, it's better to rewrite it as an exponent. So I can use my definition of a log to rewrite it as an exponent going the other direction, right? Back over here, we had exponents. We changed them to logs. Now we've got logs, and we're going to change it to an exponent just because it's beneficial for us. And that base needs to be a little bit smaller because remember, whoops, no it doesn't, it's the exponential. So the base, log base 2 goes to an exponential base of 2. Okay, now we need to know raised to what power? Raised to what power? Well, that was, what color was I using? Green for that. And it all equals the argument, which is the red stuff. X times x minus 2. So we go ahead and multiply, distribute that x. So we got x squared minus 2x equals 2 to the third is 8. X squared minus 2x minus 8 equals 0. Now we have to remember how to factor. What multiplies to negative 8 and adds to negative 2? That's x minus 4 times x plus 2. Now set each factor equal to 0. That's going to give us x equals 4. Set the second factor equal to 0. X equals negative 2. And now we better check the original problem. Back to looking at the domain of these arguments, right? X must be greater than 0. Whoops, that one already fails there. And look at this one. X minus 2 must be greater than 0, so x must be greater than 2. That doesn't cause us to reject any answers there. I mean, well, the first one got rejected, but anyways, negative 2 is rejected, but 4 is a good answer. So 4 is our answer. Thank you very much. Okay, so now go to the next one. We have 2 raised to the 3x equals 5. Now we're trying to solve for this variable in the exponential position, and very often that is done in an easier way using logs. They're inverse of each other, right? So base 2. So I've got log base 2 of 5, and that equals my exponent 3x. Well, I want to solve for x, so I'm going to divide by 3 on both sides. And there's the exact answer, but it is a little bit messy. Instead of dividing by 3, we typically write it as multiply by a third, right? Think about that. If you divide by 3, it's the same as multiplying by a third. If you divide by a half, it's the same as, if you divide by 2, it's the same as multiplying by a half. If you divide by 3, it's the same as multiplying by 1/3. Anyhow, now we've got 1/3 times log base 2 of 5. And so that's our exact answer. 1/3 times log base 2 of 5. And then the approximation, of course, we're going to need to rewrite this problem as using the base, change of base property. So I'm going to write this, and I could use common log or natural log. I'll just pick natural log. Natural log of 5 over the natural log of 2. And I think the easiest way to do this, after you get that answer, then divide it by 3. Once again, you could also multiply it. Whoops. You could also multiply it by 1/3, but don't multiply it by 0.3333. Well, 0.33. You're just going to lose some value. So it's better to divide by 3 because 1/3 doesn't have an exact decimal value in it, right? So once we do that, put it in the calculator, we get approximately, what problem is this? I wrote this down, 18. We're getting approximately 0.774. All right. Got worse looking. Okay, now number 19. Now we're getting there. How many more pages we have here? 19, 20. Oh, we got more. Okay. So number 19, we're solving this. And we're back to the beginning, really, because we've got log base 5 of x squared equals log base 5 of 36. And using the one-to-one property of logarithms says that then the arguments are equal. So now all we have to do is just take the square root of both sides, never forgetting plus or minus. X equals plus or minus 6. Now the difference with this problem compared to the other problems is that you actually have to take the negative 6. And here's why. Because when you take a look at this argument, x squared must be greater than 0. And x squared must be greater than 0 because that x is being squared, right? Because that x is being squared, can you ever, how do I say this? So what happens if you square a negative number? It becomes positive, right? What happens if you square a positive number? It becomes positive. Stays positive, I should say. So in those two cases, it's greater than 0. So really the only thing that's not going to work is 0 is not greater than 0. So anyhow, the first time in a long while is I think this is the first time that we're actually getting a plus or minus that's working with this. And that is because of the squaring, right? Because if you put in a negative 6 and square it, you're going to get 36. If you put in positive 6 and square it, you're going to get 36. It's squaring a negative, it turns into positive, and that's the reason why we have plus or minus here working. Now it says, give me the approximation. Well, that's kind of dumb because, it's already exact. You can't, we already know it's exact answer and it's a real number. Okay, so anyhow, so you put that in twice. Solve the equation. Okay, well, we're going to have to first use our property that the addition of two logs of the same base can be rewritten as log base 5 of x times x minus 7 equals log base 5 of x plus 9. Now, the one-to-one property says, those log base 5 on the left and right, therefore the arguments are equal, so x times x minus 7 must equal x plus 9. We go ahead and distribute our x, and we get x squared minus 7x equals x plus 9. Okay, we subtract x from both sides, which gives us negative 8x on the left. We subtract 9 on both sides. We get 0 on the right. So then the question is, what two numbers multiply to negative 9 and add to negative 8? That's going to be x minus 9 times x plus 1. Okay, now set each factor equal to 0, and when we do that, we get x equals 9. Set the second factor equal to 0, and x equals negative 1. We go back to the original problem, and right away from this very first one, this first argument, x must be greater than 0, so that is scratched off the list, rejected. We look at this argument, must be greater than 0, so therefore x is greater than 7. We're still good there. And our final problem right here, this is starting to look troublesome here. Are we going to have to reject? X plus 9 is greater than 0. Subtract 9 on both sides. X must be greater than negative 9. Ooh, we're okay. So x equals 9 is a valid solution, and that's the solution we type in, 9. There we go. Did we type in a solution up there? Yes, we did. Last problem, I believe. Let's see. It's a word problem. That's usually saved to the end. Yep, that's it. Good. I'm ready to call it. So, hey, let's do this one. We did these interest problems before in the exponential section. The twist here is, well, it's in the logarithm section. So what do you think is happening here? What's happening, let's go to our formula. Our formula for computing compound interest, remember that? The accumulation of the bank, right? The amount of money that grows in the bank is going to be equal to, so the amount of money that grows is going to be your principal starting amount plus the interest that you accrued. Now, if you're doing this in a compound interest fashion, it's going to be your principal starting amount times 1 plus the interest rate divided by the compounding periods That's how many times does it compound in a year. So if they said they compound it quarterly, that's 4 times, so n would be 4. If it says compound, so in this case it says compound monthly, so that therefore we know that n equals monthly, that's 12 times a year, 12, okay? So, and then we raise this to n times t, time. So just why is this in this section if it was already in the exponential section? Well, what's going to happen is they're going to give us everything in this problem except for the t. Notice where that t is. It's an exponent. And what's the best way to solve exponential equations usually is to turn it into a log, and that t becomes your answer, right? T equals, okay? So that's kind of the game plan. There's some notes for us right there if you didn't remember that formula. And let's go for it. What are they asking here? I better read it. Suppose that you deposit $11,000 into a CD today. The deposit earns 9% interest compounded monthly, so n is 12. Part A. How long will it be before the account is worth $15,000? Well, that is the future value of your investment. A is the accumulation of money. So that's the 15. There's 15. 15 just goes right in for A in this case, okay? So we're going to put that in. We're going to say 15,000 is what we're saving towards, right? Now this is the kind of problem. They didn't have much of a backstory here, but maybe it's, hey, I got $11,000 and I want to buy a better car than I could buy for $11,000. I want to buy a car for $15,000. If I put my money into a CD that earns 9% compounded monthly, how long will it take before I could buy that $15,000 car? Well, that's what this problem is really asking, that kind of thing. So I've got how much money? I've got $11,000 right now. I'm going to put that in. It's called principal. I multiply it by 1 plus the interest rate. What's the interest rate? 9%. Write it as a decimal, 0.09. Divided by my compounding periods. We already said that's 12, monthly, 12 times a year, right? Monthly. Raised to the compounding periods times t, and I'm going to make it red. Maybe I should, let's see, let me make it, what color have I done? I've made them green in the past, I guess. Let's stick with that when I change. So I'm going to keep it green, just to keep the color coordination going. So now we need to solve this nasty looking expression. Well, the thing is, that is being multiplied. I want to get t by itself. So I need to start peeling parts away legally. I'm going to divide by 1,000. Why did I pick that? Because 11,000 divided by 11,000. Did I say 1,000? 11,000 divided by 11,000 is 1, right? So I could divide both sides by 11,000. Well, you know, 15,000 divided by 11,000, it reduces down to 15/11ths. That's beautiful. And then over here on the right, what I'm going to do, I'm going to grab my calculator right now, and I'm going to take 0.09 divided by 12, enter. Okay, that gives me 0.0075. Then I'm going to add that to 1. Enter. Okay, so this stuff right here, let me get another color. This, nope, I use that color. Did I use? Yeah. So this color, oh man, green. I already have green. Well, anyways, that color, oops, I meant to do that here. This becomes what I just calculated on my calculator. It is 1.0075. Okay, so what do I have now? I've got 1.0075 raised to the 12, and dang it, I got 2 green things. That's okay. Oh man, 12t. So, I don't like all the green stuff there. But anyways, here's the problem that I have. Can you rewrite that? That's bugging me. Color is not the right color to use. So let's just do this. Dang it, I already used that color. Oh my gosh, brown. Okay, so we're going to use, this whole thing in brown became this guy right here. Okay, does that help? Nah. Anyhow, the point is, we have an exponential equation with a funny looking base, but it still is a legal base. It's still legal that we can use. So I could take that base as an exponent exponential base, and write it as a logarithm. So what is the base? It's a nasty base. Log base 1.0075. What is the argument? The argument is this guy over here, right? We've done this process many times. It's just that this has all these decimals. People get all wigged out. But that's 15/11ths. And what does this equal to? It's equal to the power, also known as the answer in this case. I guess I'll make these both green, 12t. Now we have to solve for t. And of course, all we have to do is divide by 12. Yikes. Okay, well, I need to put this in the calculator to get an approximation. It says, please round to the nearest tenth of a year. Okay, well, let's do it. Change a base. Use a common log or natural log. I'm just going to use the natural log. Natural log of 15/11ths. Then hit the enter button. Then divide it by the natural log of 1.0075. And then hit the enter button. And then once you get that quotient taken care of, then divide it by 12. And when you do all that, in some calculators you have to be real careful with your parentheses, and other calculators are, anyways, it's the makers have slightly different protocol in that. But when you plug that in the calculator properly, you will get, and I guess I already rounded it to the nearest tenth, which is 3.5. So approximately, you should have an approximate sign here, approximately 3.5 years. It'll take 3.5 years to turn 11,000 into 15,000. And I can buy that awesome car. That's, 3.5 years seems like a long time. The nice thing about this, though, is CDs, certificate of deposits, are FDIC insured. And once they make that contract with you, they have to pay you that 9%. So you will have $15,000 in 3.5 years. Now, if you went to the stock market, the stock market's been going crazy up and crazy down and all over the place. Stock market goes crazy, although it has gone up quite a bit, but it goes crazy when uncertainty is around. And, it's been more uncertain lately than ever, I think. So it's stock market to me is a little scary right now. Uncertainty with president. Well, actually, I shouldn't do too many timestamps with this video because I'll probably use it later on. But anyways, let's talk about a timestamp right now. Uncertainty with president. Well, that's pretty much decided. It is decided, but it's just craziness on the transfer. And COVID is uncertain. Well, we've got 2 vaccines, almost 3 now, so that's getting a little better. But notice once they announced the vaccine, boom, a spike in the stock market, and then it seemed like a day or two later, oh wow, there's a big spike in COVID cases, so boom, down the stock market goes. So stock market is very fickle and very sensitive to uncertainty and what happens and stuff like that. So CD is straightforward. Boom, you put that money in there. You can't touch it though, otherwise you get penalized and lose stuff there. But you are guaranteed. So I used to love CDs when they were like 7%. That was a long time ago. 9% is a dream. Right now, CDs are at something like, it's not even a whole percent. It's not even 1%. It's horrible. So in this case, with the CD rates right now, it would be, it'd probably be like 15 years. It'd be ridiculous. So let's move on. Part B. Part B, it says, how long will it be before the account's worth 22,000? Okay, it's the same problem, but we have to use 22,000. So it's 22,000 equals, whoops, I didn't want that. It equals principal, starting with 11,000, times 1 plus 0.09, divided by compounding monthly, raised to 12t. Well, we already know that this part, our first step was to divide out 11,000. Divide out 11,000, and that's exactly 2 when you divide that. And that reduces. And of course, we already found out that this is 1.0075, just like it was in the last problem, raised to the 12t. Hey, we have an exponent where we're trying to figure out the variable in the exponential position. So we could just use our logarithms. Log base, nasty base, log base 1.0075 of 2, and that's going to equal 12t. I want to solve for t, so I'm going to divide, I'm going to divide by 12. Okay, well, we just take this and write it as the natural log or common log of 2 divided by the natural log of 1.0075. And once you get that calculated, then divide it by 12, and we get approximately, what do I get? Approximately 7.7 years. So under this same situation, it took me 7.7 years to double my money. Okay, and I think that's going to do it for us. And that's our finishing touch on our talk about the stock market and CDs. Anyhow, tune in later to get more information about financial futures and things like that. And you have a great day. Take care, and we'll be talking to you soon. Bye.